Hello, I'm Oleg Borisov. We are about to start our course on modern control theory. Before getting into it, I'd like to let you know what you can expect over these couple of weeks. Control theory is a relatively young, but nevertheless mature science, which arose from mathematics and now deals with engineering applications. In this education course, I'll be discussing many of the important topics that we, as control engineers, definitely have to be familiar with. First things first, let's get started by talking about the basics. Control. What is this all about? What are you supposed to do as a control engineer? The general concepts are pretty simple. Step 1. When we address a specific application, we start determining which kinds of physics are relevant. Whether we're dealing with a mechanical, optical, chemical, or even biological application, we pick relevant equations from a proper branch of physics. Within this course, we'll be mainly focusing on mechanical systems. So we are going to use Newton's second law a lot. We'll also be looking at electrical circuits, hence we'll be exploiting Ohm's law as well. Step 2. Once we determine the relevant differential equations, adequately describing the dynamic process we're interested in, we have to design our own dynamic system, a controller that drives our process the way we want. That requires mathematics. Here we have a wide range of really different tools that we can apply. Which specific tool we are going to take from the shelf depends on the formulation of the problem. In fact, this part of the whole process represents our major activity, main concern as for control engineers. I'll stop here to mention the third step, and then I'll be right back in a minute. So finally, step 3. At the end of the day, we are in fact interested in those control systems that are automatically doing something useful for us, humans, probably releasing us from dull, unpleasant, difficult, and often dangerous work. That's why this step is very essential. If you've done a mathematical representation of the control system written on a piece of paper, then we can proceed to its implementation in a particular physical system. So, if the first step refers us to physics, the second one to mathematics, then the third one leads us to programming in terms of software and to electrical engineering in terms of hardware. The dynamics that originated from a physical foundation and were brought under control by means of mathematics is now getting integrated into a machine in a language it understands. At this point, our control system finally starts functioning, executing its mission and making our lives easier and safer. Alright, now let's get back to step 2, which is about control design. As I said, that's our main concern within this course. What are the primary control goals? Well, here they are. Set point control, in which we design such control systems that steer our regulated variables to desired predefined values, which we call references. In a more general context, these references are in fact represented by time-varying signals. And this brings us to so-called tracking control, in which we are making our system follow this time-dependent reference. I believe you know there is a tool widely used in the control industry to handle these goals. This is proportional, integral, derivative control, or simply PID control, which is indeed incredibly popular in engineering. Why? Because it is quite effective, at least from a practical point of view, and of course it is simple. However, hold on guys, it is not that easy. As we have already studied, all technical systems, they belong to the physical world. Their behavior depends highly on their own internal dynamics and on the external dynamics of the environment. So in fact, engineers designing control systems have to address a range of specific control problems, and, what is important, a truly valuable solution is not that which is only practically effective at a certain application, but that being rigorously proven by means of mathematics is guaranteed to be effective at a range of applications under the addressed conditions. This approach doesn't give a specific tool, but a whole fundamentally conformed design framework. Now let's have a closer look at control problems which are reasonable to consider designing control systems. There are in fact plenty of them. I'm going to mention just the main ones. I'd like to start with nonlinearity. There is a very basic principle in linear control theory called linearity principle. In fact, linearity is a strong assumption made to simplify control design. because the linear control theory is quite well developed, while nonlinear control theory in turn is more challenging. It doesn't have such unified and standardized tools and approaches as linear one does. However, all real-life systems are in fact nonlinear. Let's make a simple example. Input saturation. Input signals of our system, exactly those in which we send our controls produced by our regulators, are actually bounded. That means we are not able to send, for instance, infinite control. It will be saturated right away by its max value. 3 examples. In pulse width modulation, a duty cycle cannot be greater than 100%. A valve being controlled cannot be opened more than its cross-section area, and the produced rotation velocity of any motor is always bounded from above. This is all about input saturation and linearity. That complicates the control design and stability analysis once it is not neglected. Now let's talk about uncertainties. What are they about? Do you remember those differential equations that we take from physics? All of them obviously contain very specific parameters, like masses, lengths, moments of inertia, maybe friction constants, and so on. In practice, most of them are more likely unknown or just partially known, or they can be time varying and gradually change their values. This is called parametric uncertainty. But that's not all. There are still other types of uncertainties. So, structural uncertainty can be, for instance, represented by so-called unmodeled dynamics that were not taken into account during control design. It often corresponds to actuator dynamics, which is stable and fast enough so that can be neglected. There's still one more. We have to keep in mind that as many measurements we include in our control laws, the same number of sensors we must physically add in our system. There is a respected opinion, though, that physical sensors are no longer that reliable due to their exposure to environmental hazards. Therefore, the design of such approaches that reduce the number of measurements required to be fed into our controllers, especially even including regulated signals, is of high interest to researchers and representatives from industry. This brings us to a relatively new and actively developing scientific direction in control theory, that is sensorless control. By the word sensorless, we of course mean our intention to get rid of the most expensive and every-way sensor in the system. But definitely not all of them. Our controllers are still based on the feedback design paradigm. So, of course, we have to use certain sensors, but probably those which are cheaper, lighter, and easy to be integrated in our system. Let's move on and now talk a little bit about exogenous inputs. Once we design a controller, that means we already have a closed-loop system, which is supposed to be stable. However, our system can still be affected by the environment, namely by those signals that are said to be external in regard to our system. They can be called exogenous inputs, and they typically can be represented by references. Those signals we want to track, and disturbances, those signals we want to eliminate. So once again, references reflect the desired behavior of the system. If they are represented by time-dependent signals, let's recall a tracking control goal, so they should be properly compensated in order to eliminate a steady-state error caused by the derivatives of the reference. Tracking control of robotic arm is an illustrative example of a time-varying reference followed by the system. Disturbances in turn hinder the achievement of the desired behavior of the system. They are typically represented by bounded stochastic and dominated deterministic components. Their rejection is crucial in the system performance. Surface vessels are typically affected by waves, current, and wind. This is an illustrative example of disturbances that should be compensated by the control system. Finally, we have a multi-level structure of the system, which means that they have multiple inputs and multiple outputs. In more sophisticated cases, they also have cross-couplings between regulated signals that makes the system highly nonlinear. In fact, there are plenty of systems which have multiple inputs and outputs. Amongst them are such examples as robotic arms, surface vessels, quadrotors. We'll be addressing all of these, by the way, during the course. All these problems, and especially their combination, challenge scientists in control theory to design new and improve already existing control approaches to deal with them much more effectively. This continuously forms and updates content of the course Modern Control Theory. Now a couple of words about the structure of this course. It is split into two essential parts: robust control, which we'll be addressing this semester, and adaptive control, which is left for the next semester. Lecture material of the first part covers a range of concepts starting from basics such as PID control up to such advanced techniques as differential geometry. The course is practice-oriented. The fundamental theory will be accompanied with a range of modern applications as quadrotors, robotic arms, surface vessels, and permanent magnet synchronous motors. That's it. Hope you'll enjoy the course. Make sure you do your homework. I wish you luck, and let's get started.